Hello, and thank you for your interest in Metis Design Corporation. I'm Seth Kessler, President of Metis Design, and in this Tech Talk, I'll be talking about our STTR collaboration with the Department of Aeronautics and Astronautics at the Massachusetts Institute of Technology regarding out-of-autoclave curing of composite materials using carbon nanotube technology. The Metis Design Corporation is a small technical consulting firm headquartered in Boston, Massachusetts, that offers novel, multidisciplinary defense and aerospace solutions. Our areas of expertise include structural health monitoring and using carbon nanotubes to enable multifunctional materials. Our diverse staff of engineers combines solid fundamental principles with many years of hands-on experience to provide unique approaches to complex problems. We have participated in more than 50 SBIR efforts since 2002, many of which have led to successful commercially transitioned disruptive technologies. Some of our licensed innovations include a distributed damage detection network and a lightweight electrothermal de-icing system, in addition to a spin-off company that focuses on hybrid power generation. Simply put, the goal for this STTR program was to reduce the cost of making quality composite parts by eliminating the use of an autoclave. This must be accomplished using a method that's compatible with standard autoclave prepreg materials, such as IM78552, commonly used by NavAir, and the resulting components must retain mechanical properties that are typically achieved when using an autoclave to cure. The program was sponsored by PMA 262 for the Triton MQ-4C. However, similar challenges exist for nearly any DoD application that uses composite materials. Our goals were to reduce manufacturing costs by up to 50%, to reduce cycle costs by up to 40%, and to provide the ability to cure larger parts in one cure and maintain more uniform material properties, which has the potential to reduce safety factors. Traditionally, composite components are cured convectively inside of an autoclave. An autoclave is a pressure vessel that serves two purposes. First, to act as an oven to heat the polymer resin inside of a composite prepreg. Second, to apply 100 to 200 psi of pressure to consolidate the plies in composite laminate to eliminate voids due to trapped air. While autoclave curing has been the gold standard for fabricating aerospace-grade composite components, it is quite energy inefficient. The autoclave must heat the entire volume of air inside the pressure vessel, which in turn will heat the composite part, and the large metal tool used to shape that part, which is sized to withstand the high pressure of the autoclave. Under this STTR, we developed a convective approach to curing composites, using carbon nanotube heaters applied to one or more surfaces of the laminate. Since we are directly heating the surface of the laminate, orders of magnitude of power can be saved, which scales with the surface area rather than the volume of the part. Pressure can also be eliminated by removing voids through the control of resin viscosity, which can be achieved effectively since CNT heaters can ramp temperature much more quickly and accurately. As an example case study, for a 1.8 meter semi-spherical dome, such as a ray dome, an autoclave cure would consume 6 megawatts of power compared to 6 kilowatts consumed in conductive approach. Further, there's the potential for much more uniform material properties since convective curing is notorious for being non-uniform. Just think of the heat distribution inside of your own kitchen oven and then extrapolate that over a volume that would be able to fit an aircraft component. So aside from being greener, why is this energy reduction significant? We have found multiple studies that have illustrated that the energy cost for operating an autoclave contributes to between 25 and 50% of the total fabricated cost of an aerospace composite part. So by reducing the energy by multiple orders of magnitude, that cost line item is effectively eliminated. In addition to the energy savings, we have also demonstrated as much as a 40% reduction in cure cycle time, which would further reduce overall energy consumption, as well as reducing the component fabrication cost directly. This can be achieved by accelerating the temperature ramp rates using CNT heaters and eliminating much of the time it takes for heat to get to the surface of the laminate. Once the laminate surface is heated to the desired temperature, the cure process is the same whether heating convectively or conductively, as it just reduces to a simple 1D thermodynamic problem. However, in an autoclave, considerable time is wasted in heating the air and heating the metal tool, and much more time must be spent dwelling at the gel temperature, where most of the air is removed, to make sure the laminate has isothermed at that temperature before further increasing the temperature to allow matrix cross-linking to start to occur. On this slide, you can see a side-by-side comparison of a traditional and modified cure cycle, a cross-section of an out-of-autoclave cure stack-up, as well as an IR image of a 1 foot square composite CNT heater. During the course of this STTR, we have thus far fabricated composite laminates using this conductive out-of-oven approach, including our modified cure cycle of up to 60 by 60 centimeters and up to 8 millimeters thick. Our collaborators at MIT have thoroughly characterized these laminates, including degree of cure via DSC, void content via micro-CT and SEM, and strength via hundreds of short beam shear tests. Across the board, they've been able to demonstrate that the resulting laminates are void-free and maintain or exceed mechanical properties as compared to baseline autoclave cured laminates. Presently, we are roughly in the middle of our phase 2 effort. We recently completed a series of ASTM tests conducted at an independent third-party test house, including short beam shear, tensile, bearing, compression, open hole compression, and compression after impact. All results verified that our modified cure approach results in components with comparable mechanical performance as those cured traditionally in an autoclave, just at a fraction of the time and cost. In fact, these most recent results actually showed between a 5 and 20% improvement in all properties investigated, including a change to a more favorable failure mode for many of these tests. Our next steps include working with PMA 262 to use this approach to cure a leading edge section of the Triton UAS to demonstrate the process works beyond just flat laminates. Further, we will conduct some durability tests, including for fatigue, delamination toughness, and hot-wet performance. So to summarize, we're using flexible nano-engineered surface heaters that can either be directly applied to the surface of a laminate or integrated into low-cost non-metallic tooling in order to conductively cure quality aerospace-grade composite parts outside of an autoclave or oven. The key benefits include up to 50% reduction in cost due to tremendous energy savings and a faster cure cycle that allows for better manufacturing throughput. Further, by eliminating the need for an autoclave or oven, this process removes a major limitation on the size vendors can produce, as well as greatly reducing the sunk costs associated with purchasing autoclaves and traditional metal tools, which will translate to more vendors being able to competitively bid on fabricating composite components, which should also reduce the cost to the government. Finally, since this approach uses low-cost tooling, it opens up the possibilities for more iteration of composite part design and testing, both at the prototype and production stages, which is not possible today, since tools for aerospace composites can cost up to $1 million and take months to machine. Our current objective is to find additional programs of record that are interested in exploring this technology. This could really be any application that makes use of composite material. New programs would explore the application of this technique for specific geometries, specific material systems, or for specific test criteria. Our current program is only addressing 350 Fahrenheit curing thermoset composite systems, but we have also had independent success looking at curing higher temperature thermoset laminates, processing thermoplastic laminates, and using the same approach for curing ribs to skin in secondary cures. We also are involved in complementary efforts using CNT technology to improve the static interlaminar performance of composite materials by as much as 25%, and improving the fatigue life by up to a factor of 10, as well as using the same CNT heating technology for integral de-icing that we've demonstrated for both fixed-wing aircraft as well as for rotor blades. Thank you for your time listening to this Tech Talk. Hopefully, I've sparked your interest in this exciting technology. As someone who has worked as a composites engineer for over 20 years, I can tell you this is a game changer. For more information on this or any of the other technologies being developed at Metis Design, please visit our virtual booth. I'll be available for the duration of this FST event to answer your questions via video or text chat. Of course, you can always visit our website anytime at metisdesign.com.